Okay, thank you very much. I want to speak a few my thoughts about DEM from topographic maps. Is it as good as DEM from LiDAR? I think everybody has own thoughts about it. Digital elevation models are commonly used in earth sciences, and we all know about it. We have many different kinds of models, but their quality is not always sufficient for conducted studies. If you talk about the local scale, sometimes resolution 25-30 meters is usually too low. For this reason, high resolution models must be used. As we know nowadays, the most accurate high data for creating high resolution DEMs are ALS or LiDAR data. Unfortunately, we have not always such kind of data for our areas. And topographic maps come to our rescue because they are an extremely valuable source of information about the heights and nature of the relief of a given area. Contour lines, height points, water bodies, that's all great material for creating models. The main goal of my study was to carry out investigations into the quality assessment of DEM derived from topographic maps for geomorphology, maybe for geomorphometry purposes. I tried to answer the questions: what is the vertical accuracy of TopoDEM versus LiDAR DEM? And can a TopoDEM produce similar results for geomorphometric analysis to LiDAR DEM? To answer these questions, I've made comparison of elevation differences between a TopoDEM and LiDAR DEM. I've done calculations of basic geomorphometric parameters, and I conducted landform classifications using topographic position index. The source data: on the left we have TopoDEM, and on the right side we've got the LiDAR DEM. Source for the TopoDEM was 4 sheets of topographic maps in 1 to 10,000 scale. It was over 700 kilometers of contour lines, 362 height points, water courses, and all reservoirs. I decided to build them with resolution of 10 on 10 meters because if the smallest polygonal object on the map, topographic map, in 1 to 10,000 is 1 on 1 millimeter, so it's in reality 10 on 10 meters. TopoDEM was made in Polish coordinate system, and I used ArcGIS software for this, and I used Topo2Raster tool. It's based on a new DEM algorithm developed by Professor Hutchinson. As we know, this technique creates hydrologically correct DEMs. And the next source was LiDAR DEM, digital elevation model derived by ALS scanning, 1 on 1 meter horizontal resolution and vertical accuracy of 20 centimeters in the same Polish coordinate system. The source data used to create this DEM were LAS files. Every LAS dataset file contains an average 7.5 points per square meter for entire area. So it was very good material. If we are talking about methods, that was 3 major steps. First, preliminary visual assessment based on topographic maps. Observation of the model in a 3D view with a topographic map draped on a DEM. The course of contours generated from the model was compared with original contours from topographic maps, and 100 checkpoints were randomly generated for which elevations read from topographic map and from the TopoDEM were compared. The second, the juxtaposition of altitude accuracy with field measurements. Vertical accuracy is one of the most important features of DEMs. Sometimes accuracy assessment of a DEM is carried out by comparing DEM points and reference checkpoints. And as American Society of Photogrammetry and Remote Sensing recommends a minimum 20 checkpoints in each of the major landform categories, so I used almost 150 points for entire area. I used precision GPS RTK Leica Viva CS10 with average accuracy horizontal, it was 1 centimeter and vertical 1.3 centimeter. And the third part was comparison of the elevation and geomorphological accuracy with LiDAR DEM. LiDAR DEM was my reference DEM because of its very high precision. And I wanted to check the relative or geomorphological accuracy, which defines a general situation of the topography of a given area, which shows us important relief features. Apart from parameters derived from DEM, the classification of landforms was made. And as I said before, I used for this topographic position index a very simple classification system. It means that it's a difference between a cell elevation value and the average elevation of the neighborhood around that cell. The study area is in Poland, in southern Poland. It's the black point in a Silesian Krakow upland, which belongs to the strip of Polish uplands. The area covers about 80 kilometers square. Local relief is 136 meters. It's a moderate, little hilly relief. The highest places are Parcina Hill and St. Dorothy Hill. It's more over 300 meters. And the lowest places is on the southwestern part. In this place, it's all called area. There are a few different types of landforms. The topography of this place is well recognized because it's near my living place. And if we're talking about results, first of all, visual evaluation of TopoDEM model in 3D showed that created TopoDEM reflects the general character of the morphology of the study area very well. Even some details of the relief related to the human activity were visible. I generated and compared original 10-meter contours from the model. It's on the right here, and on the left we can see the original contours from the map, and we can see that the course of the contours it's almost the same. And 100 checkpoints were randomly generated for which elevations from the topographic maps were read and compared with elevations obtained from the TopoDEM model. The differences was not so big. It was from minus 1.6 meter to plus about 2 meters. And values of mean absolute error and root mean square error were about 20 centimeters, and standard deviation was only 40 centimeters, and it is a very good outcome. Next thing, elevation differences between TopoDEM and LiDAR DEM. When we look on the histograms with elevations, we can see typical right skewed positive distribution. It's a very similar distribution of the heights. Next, results of elevation differences between TopoDEM and LiDAR DEM. There are two very big errors. The negative maximum error was minus 20 meters, and positive maximum error was plus 22 meters. It's very big, but it was only it was some kind of outliers, because there was a very nice small mean absolute error, 1.1 meter, and RMCE 1.6 meter, and standard deviation less than 2 meters. And the largest elevation differences, it was related to the strong human activity, and the topographic map was from 20 years, and LiDAR DEM is from about 3 or 4 years ago. Some researchers noted that the results substantiate the finding that the accuracy provided in form of RMC alone is not sufficient to assess the quality of all DEM. So I decided to calculate the result conformity of elevations between two DEMs, which I proposed a few years ago. This method consists in comparing both DEMs cell by cell and calculating the differences between them. And here result conformity values express how many percent of the topodem grid cells are in accordance with the same grid cells of LiDAR DEM. And conformity was calculated for different elevation ranges, as you can see, 10 centimeters, 25 centimeters, half meter, 1 meter, and 2 meters. And as you can see, differences between plus or minus 1 meter, it was more than 63% of all the model, and differences till 2 meters, its area almost 86%. It generally shows how accurate our topodem is. The basic geomorphometric parameters, as you can see, it was altitude, local relief, slope, curvature, and aspect. Altitude, when you can see, the values are very, very similar, and it was only one difference between minimum value. It's about 5 meters. The local relief, it was calculated in 3 different filter windows: 3-on-3, 10-on-10, and 25-on-25 cells. I wanted to check how the values are distributed. The biggest differences between the models occur for 3-on-3 cells because of much detailing of the LiDAR DEM. But in 10-on-10 and 25-on-25s, the differences are very, very small. The slope values, of course, show us the similar situation, because LiDAR DEM show a lot of small forms. So the main differences are with the highest values of slopes. The maximum values is the biggest difference, but the mean values or standard deviation are very, very similar. The curvatures were very, very interesting for me, because on the left we can see the curvature map from the topodem. And we can see the very expected values from minus 0.5 to plus 0.5. It's a moderate relief at the hilly area. And on the right side, you can see the map on the basis on topodem, and it's not so clear in this scale. We have to enlarge our map, and then we can see many details. So in this case, the LiDAR DEM map is a little bit unreadable, because too much details. The similar situation is when we look on the aspect map. The distribution of the aspect shows that the map derived from topodem is much better for analyzing, because it's much simple and more generalized than the LiDAR map. But when I look on the analysis of the polar plot and percentage, I see that it's almost the same percentage, almost the same values between two DEMs. It's very, very low differences between 0.3 to maybe to 1 or 2%, but sometimes it's statistical error. So generally, one has to state that topodem deals with this variable very well. This DEM clearly shows the course of the main ridge lines and river valleys, as well as large areas of slopes with a specific aspect. And the last thing was landform classification with topographic position index. I decided to apply 10-class landform classification, and you can see all the maps on the left. We've got from topographic map, on the right from LiDAR, and spatial distribution, visual spatial distribution is almost the same. And if we look on the percents, it's almost very, very similar, very similar. So my conclusions are: first, elevation accuracy of the analyzed topodem corresponds to the precision of the source topographic maps. And it was confirmed by GPS RTK measurements. The second, LiDAR DEM with 1-on-1 meter resolution and even converted to 10-on-10 meters is a great DEM, of course, very detailed, but sometimes for geomorphologists is too detailed. Maybe sometimes for this size of area, like me, it was about 80 kilometers square. And TopoDEM model coped well with the presentation of topography. These results confirmed the significance of geomorphological accuracy in geomorphometric analysis, in geomorphology analysis. And the last one, the above information about TopoDEM may be useful when there is no high resolution DEM derived from LiDAR. For some areas, there is a need to create a DEM of a given area based on historic topographic maps when we want to compare some information contemporary with historical data. And sometimes TopoDEM can be used as a reliable data to reduce the errors of freely available global DEMs. So TopoDEM is as good as LiDAR DEM. I don't know, it depends, but sometimes I think yes, for me as geomorphologist is very, very useful DEM from topographic maps. Thank you very much.